Professor Susumu Kitagawa. He was born in 1951 in Kyoto, beautiful Kyoto in Japan. And in 1979, he was awarded a PhD degree from Kyoto University. And then he went around a little bit in Japan. And after a while, he returned to his hometown, where he's now professor at Kyoto University. By that, please join me in welcoming Dr. Kitagawa up on stage.
It's okay. This one. Oh, here. Yes. First of all, I'd like to express my gratitude to the Royal Swedish Academy of Sciences and Nobel Committee for the honor of a lifetime. I'd like to thank everyone for being here. It's a great honor, and it's so wonderful to see my friends, colleagues, and my family here today. So let me start my talk. My talk contains 3 parts. The first one in current world. In 19th century, human created new technologies that consumed a lot of energies. That time, people used coal as energy resources. In the 20th century, liquid petroleum was used. In this century, depletion of the underground resources has become a concern. So, gas substances should play an important role. The trend is shifting from solid, liquid to the gas. So we are standing at the gas age. So this is small gas molecules. And usually in the ambient condition, the gas state, they are widely distributed and deeply related to environment, natural resources, energy, and life. However, humankind is still not in control of gases. So, our world is dependent on the underground resources, I said. So it's a crisis of depletion of underground resources and also the global warming. So we have to switch our new world to the new world. That is the world dependent on the ubiquitous resources. However, the gas substances easily diffuse and invisible, and some has short life and toxic. So it's very difficult to handle gas substances. So we have to develop new material to control these gas substances. That is porous materials. By using this, we can carry out separation, storage, and conversion. So we have to develop new technologies in this process at low energy and the ambient condition, mild condition. So let me tell you about the history of the porous materials. In the Egyptian era, people already used the porous materials, that is activated carbons. In the 18th century, the natural stone containing the porous structure were found, and the artificial synthesis, later on, the artificial synthesis of these materials strongly contribute to the current, the petroleum industries. So quite interestingly, and Alfred Nobel invented dynamite here. So he used porous materials, natural products that we say the Kyoto. And previously, I told about the importance of the gas technology. So we have to develop advanced porous materials. That the materials and the porous metal complexes I want to talk today. So about the MOF materials, so already Professor Richard Robson talked about this one. So this is constructed from the metal ions in the organic molecule. And so the variety structure we can get. So I told you about the ubiquitous gas. Air is the ubiquitous gas, as you know. Air contains the carbon and oxygen, hydrogen, nitrogen as the elements. So from these elements, we can prepare many various types of things. To do this, we have to develop advanced porous materials. We handle these gas porous compounds from the process, the separation, the concentration, and the conversion in this case. So let's move on to part 2. That is the chemistry of creating nanospace. Louis Pasteur said, chance favors the prepared mind. Not by chance, but how a questioning mind opens the door to the science. So, 3 notions behind my science. That is, number 1, assembly. Structure arises from elements. Number 2, space. Function emerges from nanospace. The third, dynamicity. Everything flows, nothing stays. Okay, first number 1, assembly. This is a lesson from the statistical mechanics and biomolecules. When I was undergraduate student, I learned the physics course. In particular, in the statistical physics, I encountered the Boltzmann equation. This connects the nano world, the molecular world, and our macro world. This is very fantastic. And the second is biomolecules. More than 100,000 human proteins arise from only 20 amino acids. This is an astonishing triumph of molecular assembly. These insights planted me in a deep conviction that structure and function arise from assembly. The second, and also when I was the student, I saw the book, The World of Genius, written by the Professor Hideki Yukawa. He is a Kyoto University professor. He awarded the Nobel Prize in physics. He loved reading the Chan-Tzu, who is the ancient, old, 24 years ago. He is a sage. And he wrote, the usefulness of the useless. This is everyone knows the usefulness of the useful, but no one knows the usefulness of the useless. It's very difficult to understand, but this is this notion impressed me. So, nothing useless. But if we think this is a space for the anion and the cations, in the low, very narrow in the system. So, this is nothing. But if we divide this space using the building blocks to give this kind of the closed space, but integrated to extend the infinity, this is a kind of porous materials. The number 3, dynamicity. This is a universal principle from philosophy of flow. So I learned the Greek philosophy when I was a high school student. I encountered the Heraclitus. He said, Pantarei, everything flows. And also I was born in Kyoto and grew up in Kyoto. So I had a lot of the historical books and so on and so forth. So mostly the concept is impermanence. And the Buddhism also said all forms arise change and pass away. These ideas form the foundation of my soft porous crystals I mentioned today. So let's start my 50 years journey. And I graduated Kyoto University, and I joined the Professor Fukui's group. Professor Fukui was awarded Nobel Prize in the quantum chemistry, and I learned this field, and then moved to the Kindai University, and then moved to the Tokyo Metropolitan University, and back to the Kyoto University. So each university initiate the development of materials based on the three notions I told you. So let's start the porous materials like this. How to prepare it? So this is the famous temple in the Kyoto University, and you see this is the big balcony. From here we can see the Kyoto city. But this is constructed from 139 Zelkova trees and without pegs. This is fantastic. In the macro scale, we can make it. What about the nanospace, nanoscale? So this is 3D imagination using toy. So in this case, we have a magnet. But do we have a magnet in the nanoscale world? Yes, we have. That's a coordination bond. Coordination bond connect to metal ions and organic molecules like this. So you have the organic molecule and solution and the metal ion solution mix. In a minutes, in a seconds, you can get this kind of framework. And also the crystal, very beautiful. For instance, this is 1 millimeter crystal. So the crystal structure like this, the unit is 1 nanometer. So the one side has 1 million channel. And the vertical side also 1 million. Totally 1 trillion channels per 1 millimeter crystal. That's enough for the absorb, the capture, the gas materials like this. So after graduation, I got a job in the assistant professor in the Kindai University, where the Professor Munakata conducted the kappa-1 chemistry. I also carried out kappa-1 chemistry. So from the theoretical field to the experimental field. So what is kappa-1? What we usually see is kappa-2, metallic kappa and kappa-2 salt and kappa-2 compound. What we rarely see is kappa-1. So unstable, elusive, easily oxidized, invisible in everyday chemistry. So this looks like a useless metal ion. But no. MOF originated from the chemistry of kappa-1. The cytosynthesizing, the long time ago, cytosynthesized kappa-1 dinitrile ligand system. That is the network structure. This is a fully intermediate system. So after that, Professor Robson synthesizing diamond-like structure. This has no intervention, accommodate ion and the organic molecules. So he also showed the network formation principle. So simultaneously, Huni synthesized this kind of interesting materials that is using the DCNQI ligand. The DCNQI ligands, has a column to show the high conductivity. This is the metallic conductivity. And so I was very interested in this system, and then we interested in the fully densely packed structure because the conductivity pathway, the dense structure is good for these properties. However, one day I tried to determine the crystal structure with my students in the Kyoto University Computer Center. The center was so crowded. I have to wait for a long time, for 1 or 2 hours, to analyze this data. In that time, we just analyzed the intermediate structure. The student said, there is a hole in this structure. I was so impressed, excited to see, because in the cavities there is an ion and also organic molecules. So this moment marked my first step toward MOF. However, mostly the cationic frameworks are synthesized so far. So the anions incorporated. And also the kappa 1 and the ligand binding energy is not so large. So this means not so strong bond. So our central question at that time is, can organic-based coordination polymer complex, the crystals possess stable nanopore that can absorb small molecules? That's the point. This is the research time flow. At the beginning, the focusing the densely packed structure, and after the event, I told you before my slide, and we focus on the porous structure. So move on to the Tokyo Metropolitan University. So instead of kappa 1, we use cobalt 2 plus ion to construct this kind of network structure. So without gas, this structure maintained the pore. So we carried out gas absorption. We are very succeed in this case. But this is very exciting original report by my student, Mr. Yoshinotomi, at the group seminar, October 20, 1995. He showed this crystal structure, and in addition, Dr. Kenji Seki, he's a collaborator in the Osaka Gas Corporation. He measured gas absorption, and he sent us the raw data by fax. This is the data, okay? So it was very exciting in that time. So this similar time, the Omayagi also synthesized this kind of robust framework using zinc and benzene dicarboxylate. So now we have this type of the robust porous materials. We call this is second generation MOF material. So thanks to these properties, there are many functionalities that many people discovered. So move on to the Kyoto University, back to the Kyoto University, where I am very interested in dynamicity. So once again, Pantalei, okay, this is my mind, in the prepared mind. So that time, our focus is the materials from rigid framework to the dynamic porous solids. Before I'm talking about this, just a little bit, I want to show an early scientific validation. The coordination structure are dynamic rather than static. The first one, when I was a graduate student, I studied this kind of dihistidyl cobalt compound. This is crystal structure, very rigid. But in solution, in the aqueous solution, this is highly dynamic, depending on the pH. The second one, I worked for the alkaton and the synthesizing dimetal complexes. So this is a green crystal, very beautiful, but just heat, this color turned to the brown. So what's happening is dimolybdenum unit rotate by heat. This is a solid, but still dynamic. So this is very impressed me. Okay, move on to the framework. So just imagine this kind of things. Framework should also flexible. So we predicted the presence of the soft framework, and we did the preliminary experiment. But soon after, the various type of the flexible structure was obtained. Here, this is the 2D system, but the mutual dislocation gives this. This is the hinge type system, and this is expandable case. And this is interpenetration, like this. So many systems have been synthesized. So the one example is our case. We synthesize using kappa 2, synthesize this kind of system. And when introduced gas, abruptly open up the gate and reduce the pressure, gate close. So what is important is this shows the hysteretic sigmoidal curve, completely different from conventional IPAC isotherm patterns. So we can distinguish the supercritical gas like this and at room temperature. If we exclude out summertime calculation, in particular in the energy in the open home and the closed home, the energy difference only 4 to 5 kilojoules per mole. So that means this is a cooperative phenomenon. So now we have 3 materials, in particular in this third generation compound. So dynamic framework is most outstanding and unique features. So we term this more generic term, the soft porous crystals. So the part 3, I'm moving. So I want to show the very fantastic functions about soft porous materials. And the first one, So there are 2 types of the flexibility. First one is the dynamic, global dynamics. The second one is local dynamics. So the first one, this is the acetylene gas. Acetylene gas is dangerous. If we compress the 2 bar at room temperature, abrupt explosion occurs. But we are so brave to accommodate the acetylene in our MOF compound. And finally, we succeeded in getting this type of the acetylene sorption and the storage materials. But for the usable material, we need to control the gate pressure. So the sorption is like this, but we have to use acetylene again. So we need to control the gate closing pressure. So what is difficult is the pressure range is very narrow, larger than 1, lower than 2 bar. How we can control this one? So our strategy is to accommodate gas molecule. The structure should change to accommodate gas molecule. So the deformation energy control is very important. So we did. Here, the interpenetrated structure, the unit has the zinc and benzene dicarboxylate and the pyridine. So control the dispersion energy. So we introduce the substituents, just like a solid solution structure. And finally, we obtained this type of beautiful sorption like this. This pressure range is larger than 1 bar and lower than 1.5 bar. Very safe storage system we can get. The second one is the local motion. And this is the difficult, the pair for separation. That is H2O and D2O. Both have the very similar chemical and physical properties. So this separation is a sort of the 100 years puzzle. And this by electrolysis, the D2O was obtained from the natural water, tiny amount, but for the industrial production, and this is the distillation, this is the electrolysis, we need to have a huge factory. It's a very energy-consuming separation system. Because the separation factor 1 means theoretically impossible to separate. Only small difference, 1.05, 1.2, even in the current system is 1.2. So we need to develop more about this mechanism, or discover this mechanism. So this is a big issue. So we synthesize this type of porous structure, big pore and the small channels, big pore, small channel. On the small channel, we put this type of the local motion ligand. So the motion is just like a dragonfly. So using this channeling system, we try to separate these materials. So this is the results. And the H2O diffuse much faster than the heavy water in our system. But usual zero lights, activated carbon, HKUST1 MOF, GIF7 MOF, and the other MOF materials show the exact same diffusion. So we succeeded in this kind of the discrimination of these materials, the separation factor up to 200 at room temperature. So this kind of flexibility, the dynamics is very important for the very difficult tasks. So at the moment, and very recently, we had a big sort of the question, because in 1997, this is very important, our materials. We carried out first demonstrated gas sorption, but without gas here, this structure, the pore size is smaller than the gas molecule here, for instance. How gas molecule accommodated in this way? This is a big issue. So we revisited these materials, and this case is the CO2. CO2 adsorbed at the lower pressure region and smoothly absorbed. And what is interesting in the second, this pressure abrupt adsorption occurs here. So we determine the crystal structure. We can see the adsorbed CO2 molecules. Why this happens? So the result, two distinct behavior coexist. That is local flexibility and the phase transition, global dynamics. In particular, in the local flexibility, and this is the narrow channel. So narrow channel aperture like this. This is constructed from the bipyridine and the nitrate gate. So bipyridine rotate like this. So therefore, this gas molecule can diffuse easily. We call this is pore squeezing diffusion. So conclusion is, our compound at 1997, born to be soft. Very interesting. Already I found, but I did not know that. So, summarize here, each university initiated the development of porous materials based on this concept. So now realize, when I was a graduate student, I thought this kind of notions. So, and here, at the beginning, I showed you this kind of the functionalities. So many researchers discovered this kind of functionality, the storage, capture, and also the separation and the synthesis on the polymer and the catalysis, and also the physical properties in the ion conductivity, in the magnetic properties, and also the optical properties, and also the different type of absorption profile. So this is very fantastic, but still the application we can expect. So because, and from the robust framework and the flexible framework, in addition, these frameworks, we are now developing this type of the hybrid MOF system, using the other materials. So this is very important for the practical use. So the keyword in the assembly, space, dynamicity. These are very, very important for in the keywords in the porous materials, in particular in the MOF materials. So we can expect the expanding this functionality more and more, and also the commercialization that just started. And good news is still now we have more than 55 startups in the world. So these startups contribute to the scale-up production and also the low-cost MOF materials. So I am the fundamental scientist. I handle only less than 1 gram materials. So for the commercialization and the transfer to the society, we need to have kilogram or ton scale materials. So it's a good teamwork from fundamental and the startups and also the society. So this is very nice, the case. Okay, so at the beginning, I told you the gas materials widely distributed and the closely related to the various aspects in the environment, energy, and also in our body control. So, even so, we need to develop new society, new world, depending on the ubiquitous materials. So, in a sense, if we can use air, so we can say the gas age is from real gold. Real gold is just gold. Right now, the price is high. All the people are interested in that. It's too short range. But the black gold is coal and the petroleum. And now it's air gold, or future air gold. We need to use air. So even in the small countries, air is equally distributed. That's very important for our future. So, and I would say in the Chanzu, at the beginning, I told you about the usefulness, useless. But he also said here, and the living by use of mist. So, what is mist? So, mist is contains the air and the water, contains everything. So, 2,400 years ago, he thought something about this, but that time it's not just a dream. But now, it's not dream, in particular in the future. So we are standing in the future, toward the future. The air gold and the porous materials, of course, in the not only MOF, the MOFs and the related MOF materials and porous materials, porous materials make our dreams come true. That's very, very important for the future. Okay, so this is my academic network. So prepared by my collaborator and the Minshu Yao, and so maybe it's difficult to see the name, but later on, please look at this. So this journey was never mine alone. It was worked together by collaborators, postdocs, students, funding agencies, institutions, and my family. My deepest thanks to all of you. Thank you very much.